Hello, everybody. I hope you're good. Not, not good. That was the test. Good. All right. So we will go through the memo at the end of the class, and then you are more than welcome to, with pencil, make some notes or so wherever you feel you need some marks and so, and then you can just give it back to me, and then I'll give it back to the Demis or Miss Van die Kerk. All right. So today, okay, so those of you that don't know me, I'm Gustav Potgieter. I think most of you were here in the beginning, the very first class, right? So I'm gonna go through chapter 3 and 4 and perhaps 5 or so with you, and then the semester is done. Then you can relax. All right. So any questions before we're gonna start with no questions about the test up until now. We're gonna go through it later. But any other questions that you might have? Nothing. All right, so let's go through today's class. The next 3 weeks we will spend time in chapter 3. So it will be this today, and then next week and the week after that, according to the schedule. So let's start with the work that we're going to do today. And the work that we're going to do today is, you can make the heading if you want to. Is everything about, it's undamped, but there's now forced vibration. And this including a steady state. We're going to talk about the steady state stuff. Steady state response. And resonance. So that is what we're going to talk about today. I'm not sure exactly how long the class will be. We'll see how fast we can go through the work. Right, so let's have a look at the theory and the math behind everything that we're going to do today. And then hopefully it's not necessary to remember or to memorize a lot of formulas. Because there's quite a lot of formulas in this module, right? All right, so up until now, let's just discuss what we've done up until now, or what you've done up until now. It was just a normal, let's say, a spring that we have, and some sort of mass. And we need to always just state where we're going to start. And let's say we start there. That is then the X. And all the forces, there's only that force, and that is the Kx. Let's say that force is just Kx. And we said, well, if we want to find the equation, the equation motion or motion of equation, everything down is perhaps positive. So all of your forces, there's only one. So it's a negative Kx that's equal to Ma. But the A is X double dot, right? And to write it, everything in one on the one side, we say Mx double dot plus Kx equals 0. So that is what you've done already up until now, right? So that is where it's free. It can vibrate on its own. You can say it's natural. But now what we're going to do is we're going to take the same system but we're going to say, no, there's something else. There's an extra force. There's an extra force with respect to time, so it's a function. And this force is harmonic, meaning it, let's say, go back and forth, or something like that. It can be just one quick force, but what we're going to look at today is harmonic forces. So that force, usually they will give that to you, or if they don't give that to you, you can say, well, it's a beginning force, and we know it's harmonic, so it's either sin or cos of the frequency of which that force is implied, just times t. That's all. Now, usually we're going to make use of the cos one, and the only reason, we know sin and cos is basically the same thing. The only reason why we usually use cos is because we know that in the beginning, so cos of 0 will then just be 1. So we assume that the starting position is the force that we are looking for. And like I said, this time we don't have the subscript of n, so it's not the natural frequency, it is the forcing frequency. It's a forcing frequency, that one. So that is what we're going to look at today is, all right, now that we don't have 0 anymore, we actually do have an extra force now. So if you want to get, again, all the forces, the equation of motion, we will have still negative kx, because downwards is still positive in my case. This time plus that F force, which is FO cos of WT, which is equal to mx double dot, because it's equal to MA. And we take everything to one side. So we have mx double dot plus kx, which is equal to FO cos WT. So as you can see, we don't have any damping coefficient yet. That's next week's work. So usually there would have been an extra one, and we'll talk about that in a moment. So this is a differential equation that you've done in APPM 212, and it's non-homogeneous, right? This one was a homogeneous one because it was equal to 0. This one not, because not equal to 0. So what we've done in APPM 212 was, when we are faced with a question like this or differential equation like this, we need to get two solutions, right? We need to get the homogeneous solution and then also the particular solution. You guys remember that? So the same we're going to do here. We're going to say, all right, for the particular, for the complementary solution, or let's call it the homogeneous solution. So I'm just going to say H for homogeneous. Let's see what we do. We equate it to 0, and to get that, we know we can transform it to R. So we can say it's mR squared plus K. Remember that whole stuff, if it was like this, 3y double prime plus 7y prime minus 4. You would have said 3r squared plus 7r minus 4. That stuff. So it's the whole thing about the characteristic equation and so forth. And we equate it to 0. So r squared is negative k over m. So r alone is the square root of negative k over m, but positive negative. So to write it even nicer, we say it's 0 plus minus. We don't like a negative under the root, so it's just k over mi. And just like you've studied in the maths, the moment you have a complex number as your solution, you know the complementary solution, or in this case, the homogeneous solution, will then be e to the power of that alpha, Remember, that was alpha, and this is like beta, or A and B. So it's e to the power of 0t multiplied with C1 cos of the beta, which is square root k over m, t, plus C2 sin square root k over m, t. That is the solution to a homogeneous differential equation that has complex numbers, or complex solution. But what is square root k over m? That's just the natural frequency, right? So we can, and e to the power of 0 is just 1. So this answer actually for the homogeneous part is then just C1 cos natural frequency plus C2 sin natural frequency times t. So that then is our homogeneous solution. So now we're going to have a look at how can we get then the particular solution. And then we put them together, and then we have the response. We have the final equation of the amplitudes. Any questions so far? All good. Yes. Yeah, like this, because it's a function in terms of time. All right. So for a particular solution, we need to equate it to, we need to first guess. Remember the guessing method. We need to first guess what we're going to make the particular solution. Now, because there's a cos already involved there, I'm going to use it as cos. You can use sin as well, but just to make the math easier, you use the same one that's already present. And just keep this in the back of your head. You remember from differential equations that you had, if you're going to choose something here that's already been be part here, then there's some sort of a problem, or you might get a problem. And then we need to multiply with a t and stuff like that. You guys remember? But we'll get to that. Just like I said, just keep that in the back of your head. So we have this, and I'm going to say it is some sort of number. Usually we just make x is a number, and then cos wt or omega t. So the first derivative is then just x sin omega t, but negative omega. And then the second derivative is then negative omega squared x cos wt. All right, now I need to solve for x, obviously, because this was a number I didn't have. Usually, we would have said a, that you've done in the previous years. All right, so that equation there then becomes the following. It becomes m times the second derivative, so it's negative w. I say w, now it's omega, x cos wt, plus k times just the normal x, so it's cos wt, and that must all be equal to fo cos omega t. And can you see why we selected the beginning to be cos? Because now the cos's will cancel quite nicely. Otherwise, we need to do some other gymnastics. So now the cos, all the cos's can be divided or with itself. And finally, we then have, and I can take out an x as well. I'm taking out an x. I'm left with negative m omega squared plus k. That's equal to FO. So in the end, the x, that amplitude that I'm looking for, that value, or in this case, it is just a number, just the amplitude, is then just FO over K minus M omega squared. And that is one equation that we need to know. But can you guys see where it comes from? It's nice to know what you are doing is not just something taken out of thin air. All right, so we're gonna carry on with two things now. I'm gonna carry on with this, and I want to carry on with that, and then later see how everything fits together. So let's just carry on with this, and then we'll get back to this, because remember we still need to calculate C1 and C2, because that's just constants. We need to still find the values of those two. But first, let's just carry on with this. So the one question might be, all right, but what if this forcing frequency is close to the natural frequency? What will happen? Now let's see what will happen. We can write this x just in a different form. Yeah, we can write it just in a different form. We can say, well, I'm just going to take out the k at the bottom. So if I take out the k, I have m over k omega squared, and at the top just FO. You don't have to write that step. And then take it above. So I have FO over k over 1 minus m over k omega squared. But wait a minute, what is the natural frequency? It's the square root of k over m, right? So the natural frequency is then just k over m. The natural frequency squared is just k over m. Which means I can rewrite this as FO over k, and then 1 minus the reciprocal, so 1 over omega, the natural frequency squared, times omega squared. So in the end, I have this nice formula. This is also another formula that I think is on your formula sheet, or if it's not, then it's just something that you need to remember. So this one here. FO over k. But what is FO? Well, it's the beginning. It was your spring constant times the static displacement. So what is the static displacement then? The static displacement is then just FO over k. So I can rewrite this even nicer and say it's just the delta, the static deflection, divided with 1 minus omega over omega n squared. And now I'm interested in what if that value is, that value in total is greater than 1 or smaller than 1 or perhaps 1. And we know if it's 1, we're going to divide with a 0, and we can't do that. So we'll look now. And that basically gives us the answer to what happens when the forcing frequency is the same as the natural frequency. Then the amplitude will go to infinity or negative infinity, and we'll see that. So that's why it's so important to perhaps have a damper inside. But that's next week's work. Yes. Yeah, it's just like x, but I'm not using x. It's just to say is that if you leave that mass on it's just the beginning. What is that initial, that static deflection? All right, so usually you will see in the textbooks and so, all what they do is they just divide with that delta, that static deflection. It's all that they do. but it doesn't change the form or the shape of the graph that we're going to sketch in a moment. So that's all that we want to know. Now, we want to know how this specific graphs look like. So if I perhaps make the y-axis x over delta st, and I'm going to call this the x-axis, then we want to see how does that look like. So let's see how it looks like. So if you draw this graph now, but the y-axis is then just x over delta st, and the x-axis is r, but r is omega over omega n. Just that ratio. What happens? So in other words, if I'm going to draw this now, I'm just going to make y equals 1 over 1 minus x squared. Just to get to show you guys how it looks like. All right, so if I'm going to draw that, if I say y equals 1 over 1 minus x squared, remember the ratio is the x-axis is just that ratio. Now that ratio can be either greater than 1 or smaller than 1, but it must be greater than 0, because I mean otherwise there's no force at all. The forcing frequency is then just 0. So we're not going to look at the whole graph. We're only going to look at from 0 onwards. And as you guys can see, how the graph looks like is then just that. So how the graph looks like will then just be something that goes like this to infinity, and then there is an asymptote, and then something that goes like this. And this is obviously at 1. So this tells us something, that when that ratio is between 0 and 1, then it's still positive. Everything is positive. And we'll talk about what is positive. And so it's just the displacement that's positive, which means the force and the displacement is in the same direction. But the moment it's greater than 1, it's then negative, which means they are in the opposite direction. So then perhaps their phases are out. But then there's another case. If it's exactly 1, you can see it goes to infinity or negative infinity. So, and it's impossible, something's going to break. And that is why we need next week's class. All right, but let's just discuss this graph in more detail before we carry on with calculating those C values. So there's 3 cases that we have, and we just discussed those 3, but let's just make it a bit more formal. We have this section here, and then we have that red section there, so exactly there, and then the rest is just, let's say, the purple part. So we have 3 cases. I'm just going to call it case 1, and this one I'm going to call case 2, and that red part I'm going to call what happens if it's case 3. And how does just to explain what's going on. Any questions so far? Everybody good? Yes. Is that ratio is then greater than 1. So here, that ratio in the blue part, that ratio is smaller than 1. That ratio is greater than 1 in this purple part, and at red it's exactly 1. Yeah, for that to be 1, those 2 needs to be the same. All right, so let's have a look at the blue part first, the case 1. So for case 1, we know that the forcing frequency and the natural frequency is smaller than 1, but still greater than 0. Must be greater than 0. And which means if you take your, if you look at your y-axis, that means your displacement basically must be positive. And we can see that displacement is obviously positive. Now, if it's positive, it means that my particular solution that remember, we technically guessed this value. Just like in differential equations, we sort of guessed that value. It works out nice that is that value, but we're going to look at what should we do, especially when it comes to that part. So for this, the value remains positive because everything is positive. So it's just x cos omega t. And all what that means is my force that I have. Remember the force in the beginning I said is FO cos omega t. That's just a positive cos graph. And my XP graph, this part here, let's just make it smaller. That part there is also positive, also a positive cos axis, cos graph. So everything is nice. Everything is in the same direction. The force and the amplitude is in the same direction. And that is case 1 from that graph. Everybody fine still? All right, let's have a look at case 2, and then we'll get to case 3. So for case 2, we know that the omega over natural frequency is greater than 1, which means my amplitude divided with the static deflection will be smaller than 0, because it's this part. It must be smaller than 0, which means it's negative. So my particular solution should have been negative x cos omega t, which means my force remains the same. Remember, my force is still FO cos omega t, so it's still a positive cos graph. But now my XP value, my particular solution for the movement, will then be negative. So it's then just a negative cos graph. And that's why it's not that big of a problem, but it's just in opposite directions. Yeah, the response is then just negative. And then let's have a look at what the red part, the case 2, how that looks like. So for case 2, that is then when omega over omega n is exactly 1. So what happens then? Well, we know that value will then go either positive or negative infinity, which is a problem, which it can't be. And this means if we want to select a particular solution, just like you've done in differential equations, like I said earlier, I said just keep it in the back of your head. That means we should have multiplied, or now we need to multiply with another t. So if I'm going to do that, let's just make it another constant, t, and then let's say sin. We can say cos as well, but let's just say sin, because we know cos was already involved. So now I'm opting for sin. But it's just to illustrate this next graph. So this is a linear part. This part here, that means there will be lines like this. And then it's a normal sin graph. So this graph will look something like this. So this XP graph will look like this. And we can see the longer we go, the higher the time, or the longer the time, the more, the higher or the greater the magnitude of the amplitude. And obviously, then you sit with problems with the machine. All right. Everybody's still good. Right. So that's some of the graphs that's important, or that's nice to know. Yes. For example, that reach. Yeah, and then it will break because the amplitude is getting higher and higher and higher, and somewhere it will break because the math shows that amplitude wants to get to infinity, but I mean that bridge can't go to infinity, so somewhere it will break. All right, so let's get back to where we're going to calculate C1 and C2, and then we're going to tie everything together and then do some questions. So at the end, we have everything that we need. So the final solution for the response is then the homogeneous part that we already calculated plus the particular part. Now remember, we said the particular part we chose to be x cos omega t, but x we already found earlier. We said x was this part here, right? So I'm going to just divide, delete that part. So that is then the answer to what is the response equation. But still, I want to calculate C1 and C2. I don't have C1 and C2. I want to calculate that. So we can just say the initial conditions at 0. So basically, when t is 0, we call it XO, just the beginning. Then we will have C1 plus 0 plus FO over K minus M omega squared. So this means C1 is then just XO minus this part. So there we have C1. And to calculate C2, we can perhaps first get the first derivative of that equation. The first derivative of that equation. And it will be negative omega C1 sin, omega n. Omega n t. So we shouldn't get confused between omega and omega n and stuff like that. And I'll say something about that in a moment. Plus omega n C2 cos omega n t. And then just minus, that will become negative. So it's negative FO omega over K minus M omega squared sin omega t. All right, but we have let's test now. If I'm going to take the beginning, I'm just calling that XO. Then we will have 0 plus omega n of C2 and then just minus 0. So finally, C2 is then just x dot in the beginning divided with omega n. And that is also, let's then just write the final answer. That means xt is then C1, which is xo minus fo over k minus m omega squared times cos omega nt plus C2, which is x dot in the beginning divided with omega n sin omega nt, and then just plus fo over k minus m omega squared cos omega t. And that is the final answer to the response for something that doesn't have a damper yet. Now, but we want to write this in a better way because we want some other two graphs that we're going to construct in a moment. So we're going to discuss that just now. I would just like to mention that this part, as you guys can see, has to do with the natural frequency, right? Yes, I know that is the forcing frequency, but that's just a number. In terms of the function, it is it's just a natural frequency part that's important. So usually we call it the natural part, or you can say the homogeneous solution. And that is the part that you will see next week will eventually fade away as we put a damper in. So then the initial conditions will fade away and we will basically end up with the force that we implied. And we will discuss that just briefly now, but that's just to perhaps get you excited for next week. Or you don't get excited about classes anymore. Is there any class that's nice? Nothing, just the practical stuff. All right, and this part here, that is then the force. The force part, or you can say the particular. Just like I've discussed earlier, the particular part. All right, now I'm just going to put this on this side because I want some space. So what we're going to do now is I'm just going to try to reorder this so that it's a bit nicer. Now, you guys remember the compound angles when it comes to the identities of sin and cos that you've studied in grade 12 in matric? We know that we have the following. If we have cos of an angle and cos of another angle minus, or let's say plus, sin of an angle and sin of the other same angle, then that is the same as cos of, then those two just subtracted from one another. You remember the compound angles identity of cos. Now, from this green part, what do you see? This is just a number. 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 And then I have that cos part, and I have that sin part. You see? So I'm going to make that. I'm going to say this can then just be written as some sort of number, A, whatever that A is, then cos of omega nt minus another angle phi. and then plus FO over K minus M omega squared cos omega T. So that whole green part is basically summed up in that. And then this pink part is still just present there. And you will see in the textbooks, they write it in another form as well, but just to show you what they've done basically, is just what they are doing is they are just dividing, they are basically just writing that part that we already discussed. Let me just zoom out. This part here, we already showed what can it actually be written as. And we saw it can be written as that part there, right? It's the same thing. That and that is the same thing. So we can then just write it as the static displacement divided with 1 minus omega over omega n squared. And I'm showing you this that just to show you that there's a different way of writing the same thing. Now to tie the left-hand side and the right-hand side together, we will have a look at how the graphs look like for this xt now. So again, I'm going to make it in blue for case 1. So for case 1, where the W or omega over omega n is smaller than 1, we have xt, that's equal to a cos omega nt minus phi plus this part. And let's just leave it at that last written part. 1 minus omega over omega n squared cos omega t. Just want to make some distinction between these. All right, now how will such a graph look like? And I'll show you later on visually, but let's just try to figure it out ourselves. Right, so what we are interested in here is the part that's basically, you'll see that it's two graphs together. So it will form a, if you look from, let's say, if you zoom out, you will see some sort of form, but within that form, there's still another function. So it's two functions combined. Now this part there, that is the one it will follow. So it follows a cos graph. But then this part here is also a cos graph. So within this graph, if I can say it like that, that dotted line, we have a cos graph. That looks something like that. Where is that now? Oh, it took it away. Let's just write it. So it goes like this. So that is then how that graph will look like. And then for case 2, where the omega over omega n is greater than 1, then obviously this part here, let's just put it here in purple. Then that part there will be negative. This will then be negative, right? Because, let me just show this. For case 1, that part will be positive, but for case 2, this part will be negative. So that dotted line will then actually be a negative cos graph. So this graph will look something like this. It will be a negative cos graph, but still a cos graph within. Something like this. And that's about all the graphs and everything that you need to know of this work. We're going to do some questions in a moment, but we've basically covered everything. Yes. Well, you will see it will greatly help you. Later on, we're going to do some questions. It will greatly help you. Then you don't have to memorize stuff and know which one to put where. You can automatically derive it. But you can also just use the formulas that's already been uh, basically derived. All right, I would just like to show you how these type of graphs look like. So if I draw this graph, I just took some uh, random values because a is just a number, a is just a number, uh, omega n is just a number, uh, phi is just a number. Everything is just a number. You get the idea. It's just that t which is in terms of x. So I just draw something here, and this is now exactly as you can see the type of graphs that we will see. The amplitude for that K part. What was that K? It was that, I didn't take that. I think I took the other one. Let me just, I took this one if I'm not mistaken. This one, yeah. So the force is now that F, so the greater the force, obviously the wider that becomes. But as you can see, the phase, I think I made that P, the phase, it basically moves left and right. It's difficult to see that it moves left and right. It seems as if it's moves left and right. And then what I want to show you is that basic curve. Let's just make that P still 0. So there's that course graph, as you can see. And then I can play with this and see what happens. Now, here's that omega. I want to show you actually what happens when we rather make this part just R. So if I make this just R, hopefully it will, I don't think it will. Let's make that R. So remember that R represents now the omega over omega n, right? So let's see if that R, what happens. I just want to make it a bit smoother. What happens with that R? Where is that R? Yeah. So as I'm in, if it's greater than 1, it still follows that, nothing weird. If it's smaller than 1, it's a bit difficult now. I think, oh, there's other values. But if it's exactly 1, I think I've drawn the wrong one. Let me just see if I can draw another one. So we have some sort of number. Just delete all of this stuff because I want you to see it. It's actually nice to see everything. So if we have just a y equals a number multiplied with cos, let's say nx minus p plus a number, let's just call it f over, I want that thing actually, that one. So we have y equals 8 times nx minus p plus a number, let's just call it d over 1 minus, and I'm going to make it r, and then times cos of vx. So yeah, this is what I want you to see. So let's just make this one a bit nicer. So look what this graph do when it approaches 1. So it gets a bit of more shape as it approaches 1, but exactly at 1 then it's basically it's gone, right? Because then everything freaks out. But from there on, smaller than 1, it's still fine. and then I can change the other stuff to get it into that other form. Okay, you get the idea. That is where those graphs come from, basically. Yes.
But the natural frequency always possible the force frequency average.
Well, yeah. In terms of this is the forced frequency. So that is that dotted line. So it basically, yeah, it seems so. And then at the end, that is why that beginning part we want to and let's discuss that, because in the end you can think of it, whatever your natural frequency is, if your force is quite good and still the same the whole time, eventually that thing will perhaps be like the force frequency. So it will follow then the force frequency. But let's just discuss a few things before we're going to do a few questions. And basically what I want to show you, and this is, like I said, introduction perhaps to next week, is why we need damping. And the reason why we need damping is to get rid of this part here, right? When R is 1, then stuff is weird. So we want to get rid of that. Now, and then the other question is, okay, but if there is damping now, what happens? So if there is damping, and we'll see that in great detail next week. This is just to mention something. Then we will have this equation. That's equal to something, something, something. And to get the homogeneous solution to this question or to this differential equation, that's equal to 0. Now it might be not always, but it might be, and we're gonna almost look always to the might be part, that this solution to this one is a complex number, just like we had earlier. But remember earlier, our complex without a damper, our complex value for alpha was 0. So that was 0, that part there. So it was just 1. You guys remember of earlier. Now, if there's damping, there will be an alpha. And if there's alpha, we know that xt part will then be e to the power of, let's say, negative alpha t. And then the same, let me rather just copy and paste that. Otherwise, it's going to take too long. It's basically this part. Oh, not color. Basically this part, but we have e to the power of negative alpha t there, and also, yeah, plus e to the power, it's just with this one side. E to the power of negative alpha t there. And what can you see if time increases to perhaps infinity or really large? Then this part and this part will basically fall away. And then we only have that. So eventually, if there's a damper, and we'll discuss that next week, eventually we're going to go towards what the forcing frequency does. All right. I hope everything made sense to you. Is there any questions? Yes.
We have a class on Friday.
Not on this Friday, no. Do you want class? You... I'm gonna try to do everything that we need to do in on a Wednesday, and then Fridays is for class tests and stuff like that. All right. So this is basically that you need to know from this part of the work. So if you made notes and so, then hopefully everything is good. So let's do a few questions. Up until when is this class usually? At what time? 4, 5, 5, 4, 5. Wow. Kwart voor 6. And were you here in the up until what was the longest? 4 o'clock. Okay, so 4 o'clock. We're gonna aim for 4 o'clock. Let's see. All right. So this first one, and okay, so the question might come up because maybe some of you had in your heads, but wait a minute, I just spoke about x, x, x the whole time, right? What about when there's rotation? Now the same applies. It's then just theta, and we'll do perhaps 1 or 2 questions like that now. But let's just start off with something like this. So they say here, a mass M is suspended from a spring of stiffness, and they give that, and is subjected to harmonic force. So that is that force that is going to be applied, having an amplitude of 100 newtons. So that's that FO, because that's the beginning, right? 100 newtons. And the frequency of 5. The amplitude of the force motion of the mass is observed to be 20 millimeters. Find the value of M. So let's see what we can do. So you can perhaps draw it if you want to. It's just something as simple as this. And this is 4,000 newtons per meter. And here now is a force of FO cos omega t. They didn't say what the force is. I make it cos, as for the same reasons that we already discussed. And we know that beginning force is then just K times the static deflection, right? So the static deflection is then just FO over K. So that's just to get the beginning, because we need the beginning, obviously. So it's 100 divided by 4,000. And that's 0.025. All right. And what are they actually looking for? They are looking for the M. They want the mass. So you can always, if you don't know where to start, at least you know where to end. And then you can just work backwards. So in the end, if you don't know what to do with actually anything, not just in this module, just work backwards. So if we want to get M, we know one thing that we do know about the ratio of M is the natural frequency is the square root of K over M. So we know then that to get M, it will be K over the natural frequency squared. I have this already, but I don't have this. So now let's focus on how to get omega M. So now at least I know what to do next. But what do they give me? They give me stuff about the magnitude of the amplitude and the forcing frequency and everything like that. So the forcing frequency and the natural frequency have some sort of relationship. And that relationship we spoke about earlier was this part here, right? Because I basically have everything I need with that equation. Why? Let's write it down. So x over delta st is 1 over 1 minus omega over omega n squared. Now, technically, this value here will always be positive, right? We want it to be positive, which means this value can be negative. So just to do the math correct, we can just put it in absolute value because we know eventually if the amplitude is up or down, it's still amplitude. So we don't worry now if it's negative or positive. We just want the amplitude. They didn't say anything about negative 20 or something. It's just 20. So that X is that part that I spoke about 20, that amplitude. That's that X. So it's 20, but I'm just going to divide it with 1,000 to get it into meters. The delta ST is that value that we already calculated, that static deflection. And then here I have everything. I have the omega. We're going to talk about that in a moment. But I don't have omega n. But I can calculate it in. So remember, omega was 5 hertz. So just to take that is 5 times 2 pi. So then it's just 10 pi rads per second. So they are just putting 10 pi. So that is 5 hertz means it makes 5 revolutions in 1 second. So 1 revolution is 2 pi radians. So then it's just 2 pi times 5, which is 10 pi radians per second. And now I have one equation, one variable, so I can actually solve that value there. And I don't think you necessarily get marks for a lot of steps. You know if you get or not. Because you can then just type in your calculator, right? But then you need to know your calculator. Otherwise, if you're afraid that you're going to make some mistakes, rather write out every step and so forth. But in the end, you will get this as 10 pi over 1.5, which is more or less the same as 20.9439 and so on. So therefore, I can calculate mass. Mass is the K over omega n squared. So it's that 4,000 divided with this value squared. And then that's about 9.119 kilograms. Everybody good with this example? You see, we made use of one of the equations that we derived. It was just this equation, right? This one basically, because that was the parts that were given. All right. Let's have a look at. I just want to check time because I want to do as much as possible with you guys. Let's do this next one. Everybody good with this one? I think these are some of the problems that's part of your homework, if not mistaken. So we are doing actually some of them now. So then you can just do the rest. Those that we don't get to, you can just do on your own and ask questions. So let's have a look at this one. This is now 3.11. And this is still not a rotational one. After this one, we will get to a rotational one, and then we'll see what to do then. But they say here, a spring mass system resting on an inclined plane is subjected to harmonic force as shown. So this time is given as 500 cos 25 t, which means that omega, not omega n, just omega, the forcing frequency is 25. That part there. They gave us the K, they gave us the M, and the theta and everything that's there. So first of all, dynamics, we need to draw in all the forces that will be present. So the one force will be in that direction. And that force will be K times the total distance. Remember, if you don't apply that force yet, it will stretch out a bit. So you need to remember about that delta, a static delta. So it is the static displacement plus the x that it will eventually go. That is my part. That part that it will eventually go. So it is two parts. And then there's that mass. So the m times g. But this is my x-axis, and this is my y-axis, just to make it easier. So the y-axis, and that is the x-axis. That's the positive part. So I want to set up an equation. Okay, obviously this force as well. Let's make it red as well. I want to set up an equation in the x direction. So all the forces in the x direction, positive is downward, is then that 500 cos 25t minus that k delta st plus x, and then also plus this component, this one's component in the x direction, which will be sin of this angle here, right? So it will be plus mg sin theta. We can substitute in that theta as 20. You're more than welcome to, but you'll see later on how it will actually go away. And that's equal to ma, which is mx double dot. So to just reshuffle all of this stuff, we will have mx double dot plus k x plus delta st minus mg sin theta. That's equal to 500 cos 25t. But this thing here, I could have just multiplied this k in and say it's kx plus k delta st. But what is this k delta st? It was the force that was present in the beginning, right? The force that was present just in the beginning. But it's the same as that force. So these two things are the exact same thing, those two. So those will just divide, or will just subtract from one another. Yes. Because in the beginning, if you don't have this force there, and you just leave this mass to be drawn downwards due to gravity, the force that will take it down is mg sin theta. And then the force, the beginning, that initial stretching is then just that part there. Okay. So here's that nice equation that we almost always have. In this case, we don't see a damper because there's no damping involved. And then we can solve this. Now, from here on, you can make use of the formulas that we derived, or you can just derive it yourself. For me, it's better to derive itself. Otherwise, maybe there's something that we leave out. So this is a differential equation that we need to solve. So the homogeneous part is still mr squared plus k, which is equal to 0. And it's almost the exact thing that we done earlier. So I'm just going to skip to the end. It will be 0 plus minus basically omega n I, which means that for the homogeneous solution, it will be C1 cos omega n plus C2 sin omega n. just like we've done earlier. So this stuff, we already explained how we got there. And then for a particular solution, remember, we are basically guessing. So, but we make an educational guess. Which one will it be? Cost, right? Because there's already a cost involved. So we're going to say cost and not omega n, but just omega t. So get the first derivative, negative omega x sin omega t. Get the second derivative, negative omega squared x cos omega t. Now substitute everything back into that equation that we derived ourselves. Then we have m, and then the second derivative, plus k times the function as it stands, which is equal to 500 cos 25t. Which, remember, this omega is also 25. So you could have substituted in as 25. So again, we see the cos t's will cancel. And what did they ask? They asked for the response. So that final answer, what they want is x. What is the response? And we are busy now calculating that x. So I have negative m omega squared plus k. That's equal to 500. So x alone is 500 over k minus m omega squared. And we have all the values that we want. It's 500. K is 4,000. The mass was 100. And the omega is 25. And then you have the value, a negative value. But can you see, if you are confident in what you are doing, then it was not necessary to derive all of this if you know that you know your stuff. This equation here was that equation that we had earlier. Let me just show you. You remember that equation that I circled as well? It's just this equation. What is the FO in the beginning? If T is 0, it's just 500. So there's that 500. And then K we have, and the mass and the omega. You see, I'm just showing you if you want to derive it. For me, it's better because maybe you make a mistake if you just plug and play the whole time. Yes. It is then just meters. You can, yeah, maybe that one is perhaps stronger also. You can also derive it. You can say newtons divided with Newton meters, and this will also be perhaps kilogram Newton meters, and then it's just meters. All right. I want to do a rotational one with you, and we want to discuss the test. So can we carry on, or do you want to quickly take a 5-minute break? Can we carry on? All right. So let's just do. I was hoping that we can do actually all of the problems because it's good problems, but then you have something to do tonight. Let's have a look at. I would just like to see which one here, this one there, or this one here. That one. All of them is important, but let's do this one here. Let's do this one here. Like I said, it will be nice if we can do everything, but let's do this one here. So they say here, derive the equation of motion and find the steady state response of the system shown in this figure for rotational motion about the hinge for the following data. Then they give everything to us. So we can perhaps just go quickly and fill in everything that we have. We know this is 5,000. And this bar weighs 10 kilograms. This one is also 5,000. So here we will sit with something in terms of theta. So we will see how to do this. And then basically we've covered everything that's important. And this time, can you guys see the force is not a cos, it's a sin one. So they can give that sin one. It's not to say it's always cos. And what else do we have? Right, so the forces I'm going to draw in red. If this thing is going clockwise, there will be a force going up like that. And here's also a force that will be up like that. But this M will be that part about MA, the mass multiplied with the acceleration. So that's why I'm drawing it in orange. And then this is also a force. It's all the forces acting on it. That M is like, you can say, internal force that will be present in any case. So this distance, because this K1 is going to move a distance, that distance there will then just be theta times the radius, which is A. And here, this distance will also move, or will also be something, and this will be theta times the radius, which is B. We also know that the J part is a 12 ml squared plus md squared, because the middle is not in the exact, it's not just one thing in the middle, right? It hinges here, but here's the gravity, the center of gravity. So we have a 12 m, and what is this length? Is L. But what is that d? That d is just the half of L. So this is then just a third ml squared. So there we have that already. And in the end, because they are asking for the steady state response, we know it's not going to be a big X like the previous question. It's going to be a theta, right? And so everything is just going to shift to theta and not just X. Right, but this part here also moves. So the X here is L times theta. So if you're going to derive it twice, because I need that, is then just L times theta second derivative. So I've basically filled in everything on the sketch that I want. And just again to mention that this part is sin. So I mustn't forget about that. And I'm going to treat anti-clockwise or counterclockwise as positive. I can quickly take this omega just to the right units. So 1,000 rounds per minute multiplied with 1 round is 2 pi, and 1 minute is 60 seconds. So this will give me 100 over 3 pi. So I know that is rads per seconds. Right, now we can start with everything that we want. So the equation, I'm going to look at the moment around point O. and the moment around point O, all the forces are there and everything. Just to mention this, let's say there in the middle, this is where that JO will be. All right, so from left to right, I'm going to treat all the forces. That first one will be, the force itself will be K1 multiplied with X1, which is theta A. But that's just the force. I still need to multiply it with the length. And the length is A. Because remember, I'm busy with moment now. Plus that second force is K2 multiplied with the X, X2, which is theta B, but also multiplied with the length of B. Then the other red force is the applied force, that forced force, which is FO sin omega t. But that's just the force. It needs to be multiplied with L. And all of that must be equal to the angular momentum, which the orange part is negative. So it's negative JO and then theta double dot. It's like MA. And also the mass itself. So the mass, the force is mx, that mx dot, double dot, but the double dot is L theta double dot. Just to show what I'm doing here. This is like x double dot, because this whole thing is like MA. It's just a force. But that force needs to be multiplied with the length. Does this equation make sense? Because the most important part of these questions is that original equation. Because from there on, it's just simplification and differential equations and stuff. But if that original equation is wrong, then a lot of the next steps will be wrong. Any questions regarding how I got that equation? Yes. Yeah. I've just decided the counterclockwise should be positive. So then from here on, this one will be positive, positive. This one will be negative in terms of the moment around O. That's why these two were positive, 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 and this one were negative. And all of that is equal to the total moment. And the total moment is these orange parts, which, according to my sketch, will be negative. But obviously, I'm going to take everything to the one side to be equal to 0 or the force or the moment, whatever. So eventually, everything will be as that original equation that you have about just this, M and the C and the K, that whole thing. So everything works out perfectly. Okay. So let's just get everything nice as where it should be and so forth. So just to simplify this, we have K1 theta A squared plus K2 theta B squared. I'm bringing everything to this side, JO theta double dot plus ML squared theta. That will be equal to FOL sin sin omega t. So I have this. Oh, sorry, this one is double dot. So I have this JO plus ML squared theta double dot plus K1A squared plus K2B squared times theta. That's equal to that. And that is a typical equation that you would have perhaps know the answer should be. Because this is like your M, and this is like your K. We still don't have a C. That's next week's work. And we can see it's a differential equation that's not homogeneous. So we need the homogeneous part and the particular part, and we can put it together. And for that, you do the exact same thing that we've done earlier. Now it's just in terms of theta and stuff. So for the homogeneous one, let's also make it green. For the homogeneous solution, I have JO plus ML squared of R squared. I'm just applying the differential equations methods, plus K1A squared plus K2 B squared of no R, just that. That's equal to 0. So in the end, the R will be positive, negative, the square root of K1A squared plus K2B squared over JO plus ML squared, but I, because it's negative. So it's a complex number. So it's actually 0 plus that part. So like I've discussed earlier, this is like your alpha and this is like your beta. So if I want to get a solution, I know the solution of my homogeneous solution is e to the power of 0t, which I'm not going to write. I'm just showing you that is technically what we should have done. And it's just C1 of cos of this part. Oh, sorry, that I can take out. No, it should, let me just see, it should be there. So it's just this part. T plus C2 sin that part T. So that's the homogeneous solution, or you can sometimes also refer to it as a transient solution, which will eventually fade if there's damping. But that's, like I said, next week. And the steady state is then just that particular solution. That is the steady state. And that is what we're going to find now, because they've asked for the steady state part. So to find the steady state part, we need to get the, I say, theta, let's say theta P. And what is the guess that we should make it? Must be sin or sine, right? But I'm not going to make use of x now. I'm just going to make use of another phi, some phi like theta that looks like that, but I'm going to make it just like that. But it's a big theta. And sin of omega t. So get the first derivative. I have cos omega t and omega. Get the second derivative. And I have negative omega squared. That sin omega t. Sin's derivative is positive cos. It's just the previous stuff was cos derivative is negative sin. So this one here then becomes, I'm just going to copy and paste. That whole equation then becomes the following. That multiplied with the second derivative plus that multiplied with just theta, and theta was just that. And that's equal to the other stuff on the right-hand side. And again, everything works out nicely because now the sin parts can just cancel. So we are left with, if I multiply everything in, we are left with negative omega squared JO and then that theta minus omega squared ML squared in that theta plus K1A squared plus K2B squared. I know those, it has values, A and K and stuff like that, but let's just get an equation and then later we can fill it in. And then that theta. That's equal to FO times L. So I don't have a lot of space left, but in the end, remember I just want that theta. I can factorize that theta and take everything, divide with everything. So I have FOL divided with that part minus those two others added together. So all what I've done was I've just factorized. Let me perhaps just show what I've done in the previous step. So for just the previous step was just factorizing that theta out. Then you're left with negative omega squared JO minus omega squared ML squared plus that part. And then after that, I've just divided with that whole bracket. Everybody sees. And then just a bit of manipulation stuff to get it in a better way. So now I can finally get that value that they wanted. And that's all that they wanted. They just want that steady state. Remember, this is a steady state. The particular part is a steady state part. The beginning, that homogeneous one, is the free part. So with all of those values that we have here in the beginning, let me just put that there, as well as the GO of the JO that we have. Let's fill in what the value should be. So we have 500 times 1 over 5,000 multiplied with the A is 0.25 squared plus 5,000 multiplied with 0.5 squared minus we have omega and we could have taken out omega there as well and make it even nicer. So I'm going to do that. Omega is out, it's outside. So that JO was a third multiplied with the mass, which was 10, multiplied with the length squared, which is 1 squared, plus the other greater mass is 50, multiplied with L squared, which is also 1 squared, and all of that multiplied with the forced frequency, which is 100 over 3 pi, and all of that squared. So you just plug everything in, and then you'll get a value. Very small value, but there we have it. And this is now rads. So you see, we've done the exact same thing that we've done from the beginning of the class. Getting the particular solution, getting the homogeneous solution. So in this specific question was just getting the particular solution, basically. We just needed to get theta. If they perhaps ask us, all right, but write out the final answer. then we just add the homogeneous with the particular. And then that is the complete answer. All right. Any questions regarding what we've done? Yes. Jay, for where? For this question? For? Well, for the book, it's just the mass multiplied with the length. So it's still, that's mass of 50 kilograms will still create a moment around the oak. Yeah, because it was 10 kilograms. So we can't just throw it away. It was not 0 kilograms. In the middle. You can perhaps if you want to, but there's a reason why it's on this side. It will be different if it's perhaps here. Then this spring won't be that stiff perhaps. All right, so let's just quickly discuss the memo, and then if there's any questions and so, please write it out with a pen